Forces. Now, when we discuss forces, there is one person that is more important than anyone else, really, and this man is Sir Isaac Newton. One of his famous sayings is, "If I have seen further, it is by standing on the shoulders of giants." And simply what he meant by this, and this is personally one of my favorite quotes, is the only reason he could take science further is because of what had been done before he came. One of these people were Galileo, and Newton's first law is actually based on the discoveries made by Galileo. Now, Newton was just a student at Trinity College, Cambridge. And unfortunately, when he was studying there, the Great Plague started. Now, it's not the Black Death that was in the 1300s. This was the Great Plague, and it killed about 100,000 people in London at the time. Because of this, he decided to go stay with his mother on the farm. And it was during this time of self-isolating that he started to come up with many of his ideas. One of these was he had seen an apple falling from a tree. Now, the whole thing about the apple hitting him in the head, probably not true, but we do have some information that was passed on by his niece to Voltaire, a French philosopher, who wrote down that he had seen the apple fall. And it was sort of this idea, by seeing the apple fall, and then he looked up at the moon and noticed that the moon also seemed to be falling. And he thought that these two phenomena were related, and this led him to eventually come up with his theory of gravity, or universal law of gravitation. It was while he was at his mother's house that he wrote Principia Mathematica, which still to this day is seen as one of the most important scientific works. He also created calculus to help him determine how things fell. And he actually discovered it, or created calculus at the same rate at which it's taught today. He was absolutely brilliant. And so, all of this is to say that Newton was basically self-isolating when he formulated the laws of gravity. Right, now, a force is simply an action that can be described as a push or a pull. Now, we represent forces with the unit, the Newton, obviously named in honor of Isaac Newton. We'll generally use the symbol F in equations and the unit M, which obviously stands for Newton. Note that they are both uppercase letters. Now, when you represent forces, force is a vector quantity. Now, we will get into vectors obviously at a later stage, but simply what a vector means is it is a quantity that has a size and it's always applied in a direction. So it has size and direction. We also get scalars, which only have a size. Now, we can show these by using diagrams with little arrows. And we'll obviously scale these quantities to fit on the page. One thing we must note here is that the arrow must show the effect of the force acting on the object, not the direction in which the force is coming from, but we'll look at that later. And then usually we draw a dot instead of sketching the actual object, and this is called a free body diagram. So let's look at a free body diagram. In this case, we now have a little car. The forces acting on this car, we have our force being applied by the engine. We have frictional forces on both of the tires. We have gravitational force, which is pulling the car down to earth. And we have a normal force, which is the force of the road pushing back up onto the car. So to draw this, we first draw a little dot. We then draw all the forces that are acting on this vehicle, but around the dot. So there we have our force being applied, then have a gravitational force and the normal force. Now note that these two forces are equal. That means that the car stays on the road. If the normal force was greater than the gravitational force, it would mean the car would start floating, or if the gravitational force was greater than the normal force, the car would go through the road, which is obviously not possible. We then have frictional force and the other frictional force. Now what we can do to simplify this, instead of drawing it like this, we can just draw one line representing both. Right, and now we're going to look at the effects of forces. Okay, so the effects of forces. Now, there are 5 general ones that your textbook talks about. Number 1, a force can cause an object to start moving. So, if we apply a force in that direction to the object, it will move in that direction. Number 2, a force can also cause an object to stop moving. Now I'm going to apply a force onto the Rubik's Cube, and friction will then get it to stop moving. So we apply the force, and we see that it stops. That is due to the friction acting on the object due to the surface. Then, number 3, we can get the object to change direction. So if it's originally moving in that direction, we can then apply a force to get it to move in that direction. We can also change the shape of an object. Now in this case, I'm going to apply one force in that direction on the object and the other force in that direction. And so we can see then that we change the shape of the object by applying forces in different directions. We can also get things to rotate. And so that would be something like applying a force over there that gets this thing to spin, and that then is rotating.